So the next segment will be on covalent bonds themselves. All right, so basically there are two models that we're going to talk about for covalent bonds. The first is valence bond theory, which is the classic model, and that little potential energy well, which I drew previously, would fit into the valence bond theory of it. This model is basically used for its simplicity. It has got a nice sort of visual structure to it, and it describes almost all of the circumstances that we're looking at. The issue is, though, that it certainly oversimplifies things, and it doesn't explain some of the more fundamental ways that any system works. And what we're going to do is we're going to see some examples of this, particularly when it comes to the sections on resonance, on electron delocalization. And you can basically, throughout the course, you can look for things where that doesn't really make sense the way it's being described. And it's probably because the valence bond theory model just doesn't quite stand up to the observable facts on the ground. But that's the one we're going to use, and that's the one that, as I said, most of the textbooks use all the time. So in general chemistry, when we were talking about the principal quantum numbers, the various models of the atom and how electrons are associated with it, one of the things that we came up with was that with regards to de Broglie is if light can be a particle and a wave, what about electrons? And so this is part of that. So electrons have wave-like particles, wave-like properties. And so thinking of them in fixed orbits like Bohr did was incorrect. And that's why when we're talking about orbitals and the solutions to the Schrodinger equation, it's all about probabilities of finding electrons in a volume of space. And so this again deals with the wave-like properties of it. So if two electrons are waves, if electrons are waves and electrons get together to form bonds, you can visualize this between a constructive interference pattern or a destructive interference pattern. So ripples on a lake, and when ripples meet each other, sometimes the ripples get higher, the amplitude gets higher, sometimes it just becomes flat surface. Flat surface would be when the two sides cancel each other out exactly and it just becomes flat, or these two bumps in a constructive interference pattern will increase the amplitude. So a bond being formed would have a constructive interference pattern. If it's got a destructive interference pattern, there would be no net effect electron density between the two nuclei, and so there would be no bond because you need electron density to form a bond. So this is the valence bond theory of things. So bonds are constructive interference patterns of electrons. Now, there are two basic types of covalent bonds that we'll talk about in this class. Those which involve the head-to-head overlap of orbitals. And this is easiest to depict with regard to s orbitals. And so when two s orbitals come close together, you get a constructive interference pattern, and then you get electron density that is focused between the two nuclei. This generates a bond, and the electron densities between the two nuclei, we call this a sigma bond. And because sigma bonds are formed by the head-to-head or direct overlap of these two orbitals, sigma bonds are the strongest type of bonds. If you're going to form a covalent bond, you always form a sigma bond first. If you form a double bond, the next bond being formed will be the pi bond. But the pi bond, the strength of a pi bond is not 2 times the strength of a sigma bond. So that basically tells us that pi bonds aren't as strong as sigma bonds. So the head-to-head overlap, take home is the head-to-head overlap of orbitals is a sigma bond. Pi bonds, conversely, result from the sideways overlap of orbitals. And so to form a pi bond in organic chemistry, what the orbitals that we are going to be using are p orbitals. So there's a couple of caveats to this. The pi bonds must be parallel to one another, and they must be in phase. So here's 2 pi bonds that are coming close together. Here's where the nuclei would be. Here's one lobe, here's one lobe. The shaded side is on the bottom in each case. So this will form a constructive interference pattern. Likewise, the non-shaded side is going to form a constructive interference pattern here. But you will notice that the electron density is going to be located above, above the 2 nuclei, or below and below the 2 nuclei. So when you form a pi bond, the electron density is either above or below the internuclear axis. So, but the condition is they both have to be parallel to one another, and they both have to be in phase. So there's conditions on making a pi bond that are more stringent than making a sigma bond. The sigma bond has to have a head-to-head overlap of orbitals. They have to be in phase as well. But so here's an example of 2p orbitals in which a pi bond would form, because the phase is correct and they're aligned correctly. Conversely, over here, if you had 2p orbitals which are like sort of drawn like a propeller, you would not get there'd be no net overlap, so you would form no pi bond. All right, so that's basically the, we could actually draw some, maybe we'll do that in our first class. The head-to-head overlap, p orbitals can make sigma bonds, but they're just lying on their side. They're not up like that. Anyway, we'll get to that a bit later. Okay, molecular orbital theory. So what molecular orbital theory does is it takes this valence bond thing one step further along. So an electron wave forms a constructive interference pattern which makes a bond. But the destructive interference pattern makes what we call an antibond, so an antibonding orbital. So in molecular orbital theory, 2 atomic orbitals are going to get together and they are going to make 2 new molecular orbitals. Well, all the examples we're giving, it's 2. We'll see later on, you can actually get 3 orbitals together to make a molecular orbital, or even 4. But if you've got 2 atomic orbitals and they come together, they're going to form 2 molecular orbitals. One's going to be bonding, which is lower in energy, stabilizing. One is going to be destabilizing, higher in energy, the antibonding orbital. So there's a little rule in molecular orbital theory about orbital conservation. So if you start with 2 atomic orbitals, you need to make 2 molecular orbitals. If you started with 3 atomic orbitals, you are going to make 3 molecular orbitals. So here we go. Here is a 1s orbital of hydrogen at this energy level, 1s orbital of hydrogen at this energy level. Each has got an electron in it. When you've got the constructive interference pattern, so the 2 s orbitals are in phase, it is going to form a sigma bonding orbital, which is lower in energy. So 1 electron would be up, the other one would be down. So we didn't violate Pauli's exclusion principle. And conversely, this is the new part to this whole thing, this theory, is that you also form another orbital, which is higher in energy, which is anti-bonding, where the two orbitals are not in phase. So there's no electron density between the two of them, and this is a destabilizing orbital. So as long as this system, the hydrogen molecule's got two electrons in it, it's going to form a stable bond. But this is why we don't have molecular helium, so He2, because we would have 4 electrons and we would have to fill these molecular orbitals up, just like the off-ball principle. The lowest energy would fill first with 2, and then you would put 2 up here. And if your anti-bonding orbital is filled, you've destabilized the system and the bond breaks. So in order to break any sigma bond, you have to put electrons into the anti-bonding orbital. We're going to be breaking lots of bonds in this course. It's just going to be second nature when we draw our mechanisms. But what's actually going on is that electron density, when something is attacking something else, electron density is going into the anti-bonding orbital of whatever species is being attacked. So this isn't really depicted in when you're drawing a mechanism. So, but it's one of those fundamental things which is important over the course of the material. So, yeah, just keep this in mind, that the molecular orbitals, there's a stabilizing bonding orbital, and there's the anti-bonding orbital, which is destabilizing. We can draw it with s orbitals. We can also draw it with p orbitals. So here's a p orbital, here's a p orbital. So the electron density is above and below the internuclear axis. So this is a pi bonding molecular orbital. The anti-bonding orbital, the two orbitals would be out of phase. So there'd actually be 2 nodal planes here, one across the internuclear axis, one dividing the 2 nuclei in half, and there'd be no electron density. So this would be an anti-bonding orbital. The basic convention we have for anti-bonding orbitals is you put a little star beside them, like sigma star, pi star. And so you just say pi star, and you know that that's an anti-bonding orbital of a pi bond, or a sigma star would be the anti-bonding orbital of a sigma bond. Yeah, so the take-home message is that when we're going to be breaking our bonds, electron density is going to be going into the anti-bonding orbital of whatever bond is being broken. And towards the end of the class, we're going to see that where that anti-bonding orbital is really important mechanistically. And that's it for this little section.